Hello and welcome back everyone to Aviatrix Deep Dive. In this session, I'll be discussing GCP FireNet. And as a reminder, please make sure to watch the previous FireNet session, which is a prerequisite for all CSP-specific FireNet sessions where I discussed the basics of FireNet, including the common features across all the clouds. Since GCP allows only a single NIC per VM per VPC, the transit FireNet architecture looks a little bit different. Let me draw it out. As you can see, I have drawn 4 VPC, transit VPC, egress VPC, LAN VPC, and then the management VPC. The management VPC is only used for some of the vendors which requires a dedicated management interface. When you deploy Aviatrix Gateway, then Aviatrix Transit Gateway is going to have one NIC in the transit VPC and another NIC in LAN VPC. When you deploy the next generation firewall, the firewall will have one NIC in egress, LAN, and then the management interface only when the firewall vendor requires dedicated NIC for the management. So let's draw them out. And when you deploy the firewall, Aviatrix controller is going to deploy a GCP load balancer as well. For high availability and redundancy purpose, you always deploy 2 transit FireNet gateways, and both will be in different availability domains. The minimum size of these FireNet transit gateways or for standard deployment is N1 is standard 1, and for high performance encryption or insane mode it is N1 high CPU 4. We require minimum 2 network interfaces. As you can see over here, a dedicated LAN interface is required where you will be connecting your firewall and Aviatrix transit gateways to communicate with each other. Now let's talk about the different interfaces that we have on Aviatrix transit gateways or transit FireNet gateways. NIC 0 is the management interface for all the internet traffic, and it also communicates with the controller. Aviatrix controller is the one who manages the firewall rules on this NIC. Basically what it does, it opens up 443 access from the controller in the inbound direction of these transit FireNet gateways. Any resource within this transit VPC subnet as a source can communicate with transit gateways on all the ports. That's another firewall rule that's been created by the Aviatrix controller. Another rule is created, which basically means the transit gateway is allowed to communicate everywhere. NIC 1 is responsible for communicating between the transit FireNet and then the next generation firewall through the GCP load balancer. There is a firewall rule created for the global load balancer that it can receive the traffic from everywhere. That is quad 0. NIC 1 also receives the traffic directly from the firewall interface, which is in the LAN VPC. Make sure to enable the transit FireNet functionality at the time of the gateway creation, because you won't be able to enable that functionality once the gateway is created. So 2 default routes will be created for each 0. Basically the quad 0 towards the internet, and so quad 0 towards the internet, and then a default route towards the subnet. And same thing, 2 more default routes will be created for NIC 1 and same routes. So I'm going to write here NIC 0 and NIC 1. So these are the routes that we create. When you deploy the next generation firewall, Aviatrix controller is going to orchestrate 2 load balancer. One is the UDP load balancer and the other one is a TCP load balancer, in the LAN VPC. Now let's take a look at the architecture of GCP FireNet. Up till here, I just drew the transit FireNet, which is composed of 4 different VPCs. Now let's draw out the application VPCs or spoke VPCs. We do have spoke gateways, and then their NICs will be in this VPC in different domains. They will be able to communicate with each other using the overlay which we create between the spoke and then the transit gateway as a part of Aviatrix multi-cloud network architecture. By looking at this architecture, the enterprises can take advantage of the east-west traffic inspection, north-south traffic inspection, or also the egress traffic inspection, because from the egress you will have access to the internet. Aviatrix has another architecture which we call it dual FireNet for enterprises wants to isolate their egress inspection from the east-west inspection. So the architecture is going to look similar to the one that I'm going to draw right now. So you are going to have another transit like this. Similarly, you will have and a management. Aviatrix transit gateways will be deployed, and then they will have one NIC in the transit, another NIC in the LAN VPC. There will be a load balancer, and then firewall. And if this firewall vendor requires a dedicated management interface, then the NIC is going to be in the management VPC. So this one is management VPC, egress VPC. Here is LAN VPC. This is a transit egress, and this will become transit east-west. When we have this architecture, which we call it a dual FireNet, at this point we don't need the internet access from here, and then the spoke VPCs will be connected to both transits. So anytime you need the east-west inspection, let's say when spoke 1 is communicating with the spoke 2, then all the RFC 1918 inspection, the traffic is going to be coming towards the transit east-west. So this is RFC 1918. And when the traffic is destined for internet, then all the quad 0 traffic is coming towards here. Since this is the egress VPC, we will have internet connectivity through this, and the firewall is going to have its NICs into each of these VPCs like this. You want to make sure when you have dual FireNet that you should always disable the inspection for the transit gateways, transit FireNet gateways for your transit egress, and enable the egress through the firewall on the transit egress. So that way we are going to make sure that the quad 0 will be propagated from only transit egress to all the spokes which are in the inspection policy. Build your connection policy like you used to, and also create the inspection policy as well. If you have a dual transit FireNet architecture in both multi-region or multi-cloud environment as shown here, and you would also like to provide connectivity between them, then make sure you are connecting only east-west transits via transit connectivity and filter out the default routes accordingly. Now let's do a quick packet walk. Let's assume VM A wants to communicate with VM B. VM A is in spoke 1 and VM B is in spoke 2. The local route table for VM A has the RFC 1918 summary route, which is configured by the Aviatrix controller, and it will be pointing towards one of these spoke gateways. Now, when the intention of VM A is to send the traffic over to VM B, it sends it towards one of the spokes. Since a spoke already has the tunnels created with the transit, then a spoke has the route towards the spoke 2 also. So it is going to send the traffic to transit gateway. Now, there are 2 transit gateways, so it can hash it out and it can figure it out which transit gateway it needs to send the traffic to. Let's say it will send the traffic to transit gateway 1. So, number 2, we are going to send the traffic to transit gateway 1. And for ease of understanding, let me draw another transit gateway. This becomes your HA. Primary transit gateway receives the traffic from the spoke gateway. It is going to check whether the source or destination is part of the inspection and policy or not. To make things much easier, let's consider both spoke 1 and spoke 2 gateways are all part of the inspection policy. So once the traffic reached by the transit gateway, it checks the inspection policy status, and the status is that it is under the inspection policy. At this point, it is going to send the traffic over to the load balancer using NIC 1. Now, load balancer receives the traffic. Load balancer is going to see, okay, how many firewalls do I have? And after that, it's going to hash the traffic and then sends it over to one of the firewalls going to be used as its target. Traffic is going to go to, now let me say it's going to be step number 4. From step number 4, the traffic gets to the firewall. Now, firewall is going to inspect the traffic. From the firewall, the traffic could come to any of these transit gateways, and it's not going to go through the load balancer again. Now assume the traffic comes back to the primary transit gateway again. So this becomes number 6 step. Now, transit gateway is going to send the traffic over to the spoke. Now it has again 2 paths towards spoke gateways. Now it's going to hash, and then let's say it hashed to the primary spoke gateway. Primary spoke gateway is going to receive the traffic, and since the B is available through its NIC 0, it's going to send the traffic directly over to B. B is going to receive the traffic, and it says, yes, it's destined to me. It's going to do its thing and send the traffic back over to the spoke. Once a spoke gateway receives it, it again has 2 different paths. Whether it can send the traffic to the transit or it can send it to the transit HA. This time, it sends it to the transit HA based on the hash it has. So if I'm going to write these steps with a different color, so that one becomes the 7. Now, step number 8, returning traffic. The transit receives the traffic, and then it's going to check the inspection policy again. inspection policy is there, it's going to send the traffic to the load balancer. Now, load balancer, since it's maintaining all the hashing of the firewalls, its backend or targets, it's going to send the traffic to the same firewall. It's going to inspect the traffic and sends the traffic back again to the transit gateways. Transit gateway receives the traffic and sends the traffic after doing its hashing to one of these spoke gateways. When the spoke gateway receives the traffic, it will send it over to the VMA using its NIC 0. That's how you complete this traffic flow. Packet walk of egress traffic inspection is almost identical, except you need to turn on egress through firewalls feature. That will advertise quad 0 route to all the inspected application spokes and VPC routing tables. Traffic will follow this default route to get to the application spoke gateway and then to the transit FireNet gateway. FireNet gateways will check if the inspection policy is configured for the source or destination spoke gateway, and if it's true, transit FireNet gateway will redirect the traffic to the load balancer. Load balancer will perform its hashing and select a firewall for the inspection. Firewall will inspect the traffic as usual, but this time firewall will also net the traffic and use its egress interface, NIC 0, to reach internet. Alright, so let's talk about the firewall health monitoring in GCP. The GCP ILB or load balancer is providing the load balancing mechanism using the HTTPS from the load balancers to the firewall. GCP has a fail open mechanism on the ILB, which basically means if GCP load balancer failed to receive the probe response back from all the firewalls, then it's going to consider that the health of the firewalls are fine and it will continue to send the traffic. It could lead into the black holing issues too, but it only happens when it fails to receive all the firewall responses, the probe responses. Aviatrix provides two different mechanisms of hashing in GCP. 5 tuples is the default mechanism, and 5 tuples means source IP, source port, destination IP, destination port, and then the protocol type. Aviatrix also provides a 3 tuples solution for some legacy applications too. GCP documentation is a little bit confusing when it comes down to the hashing that the load balancer provides, and because of that, on the Aviatrix controller, you will see the 2 tuples instead of the 3 tuples. And in reality, when you configure the 2 tuples from the Aviatrix controller, it's basically a 3 tuples hashing. Controller orchestrates the hashing of the ILB, so you don't have to do anything on the GCP side. The state column on the Aviatrix controller basically tells you the state of the VM itself. It does not tell you the state of the probes, whether the load balancer is receiving the probe or not. In order for you to find out about that, you have to go into the GCP console and then go into the network services and load balancing. All right, now let's discuss the failover mechanism in GCP. GCP load balancer is sending TCP 443 probes to all the firewalls every 5 seconds. And if it fails to receive 2 TCP probe responses, then it's going to declare the firewall dead. And when that firewall sends the probe response twice, like 2 probes, then GCP load balancer is going to consider that firewall healthy again, and it's going to put them again into the pool. Only failed firewall is going to be removed from the ILB. All right, so that's all I have for GCP FireNet. In the next session, I'll be discussing OCI FireNet. Thank you very much for watching.